Okay, I think I'm stopped at this stage in my last class. Okay, so now let's move on to the next concept, that is pre-radical mechanism at an aromatic substrate. Pre-radical mechanism at an aromatic substrate. Let's give an entry, Pawan Kumar. Okay. Free radical substitution at an aromatic substrate. So this, let's give an entry, Varshita. Okay, right. Now, uh, free radical mechanism at an aromatic substrate. Here, I am taking benzene as the aromatic substrate and acetyl peroxide. So this is an radical initiator. So what will happen? Initially, there will be a so this moiety undergoes homolytic cleavage, initially giving rise to acetyl radical formation. This acetyl radical formation further undergoes homolytic cleavage between the methyl group and carbonyl carbon. So that means carbon dioxide. So carbon dioxide is one neutral molecule, and methyl radical is the species. This methyl radical, it's an intermediate, it will attack the benzene. So it will form an intermediate radical, and this radical is stabilized by resonance, and later on at the end there will be a loss of hydrogen. So by going for homolytic cleavage between the carbon and hydrogen, so giving rise to toluene as the product. So for example, how do you convert a benzene to toluene? Means it is possible just by treating with the acetyl peroxy radical. So this group, COCH3 group, is called acetyl group, and this is a peroxy. Let's give an entry, Mohan. Okay. Right. So it is possible to convert benzene into toluene. Let's give an entry, Annapurna. Right. Okay, benzene, it is possible to convert into toluene by treating with the acetyl peroxide. So this one is the reaction, and if we are looking into the mechanism, so acetyl peroxide initially undergoes homolytic cleavage between the two oxygen, giving rise to acetoxy radical. This acetoxy radical further undergoes homolytic cleavage, giving rise to neutral carbon dioxide. It's a gas, it will go out. In addition to that, a methyl radical is formed. This methyl radical react with the benzene, more particularly the pi bond undergoes homolytic cleavage and forms with the methyl radical, giving rise to benzene radical. This benzene radical stabilized through resonance, and at the end loss of hydrogen radical, giving rise to toluene as the product. Let's give an entry. Right. Okay. So this is about what is called as how the benzene is converted into toluene. So let's look into the few more examples. under this category. So benzene, when it is treated with benzoyl peroxide, again benzoyl peroxide is a radical initiator. So what it will do? It will create a phenyl radical. How the phenyl radical is obtained? By the homolytic cleavage of benzoyl peroxide. So that means this is the structure of benzoyl peroxide. So it undergoes homolytic cleavage between the two oxygen atoms, giving rise to benzoic acid peroxide. This is the benzoic acid peroxide. This benzoic acid peroxide further undergoes homolytic cleavage between the phenyl and the carbonyl carbon, giving rise to phenyl radical. Phenyl radical react with benzene, so giving rise to a radical intermediate. This radical is stabilized by resonance, and at the end there will be a homolytic cleavage of CH bond, giving rise to biphenyl as the product. So how do you convert a benzene into biphenyl? It is possible to convert a benzene into biphenyl by treating with benzoyl peroxide. So with this, I will go to the next slide. Okay, so next slide, I am taking free radical substitution mechanism in allylic halogenation. So CO, CH, double bond, CH2 group, okay. Up to this group is called allylic position. This carbon is allylic carbon, this proton is allylic proton. So allylic proton containing compounds, okay, otherwise allylic allyl compounds, okay, allyl compounds undergo halogenation with NBS, N-bromosuccinamide, or N-chlorosuccinamide, or N-iodosuccinamide, giving rise to halogenation at allylic position. So this position is called allylic position. What is allylic position? Next to the double bonded carbon. Next, this is the double bonded carbon. That means this C double bond C. Okay. And these carbons are called vinylic carbon. This is vinylic carbon, this is also a vinylic carbon, and this is the allylic carbon. Okay. So, right, allylic position can be halogenated by using NBS, N-bromosuccinamide, N-chlorosuccinamide, NCS, NCCl, NCI means N-iodo, N-I-succinamide, NIS, okay, NIS is N-iodosuccinamide. So heating is required, and solvent, carbon tetrachloride, it is a non-polar solvent, that's also required to convert a allylic position, this is a allylic position, into a halo at allylic position. Otherwise, what we can say that halogenated allylic compound, halogenated allylic compound. So what are the halogenating agents used? NBS, N-chlorosuccinamide, and tertiary butyl hypochlorite. Tertiary butyl hypochlorite is also used as a chlorinating agent for converting an allylic position into chloroallylic compound. So with this, I will take, this is an example, I will take mechanism in the next slide. So this is the structure of N-bromosuccinamide. N-bromosuccinamide. N-bromosuccinamide, when it is subjected to heat or light, and when it is subjected to heat or light, what will happen? There will be a homolytic cleavage between the nitrogen and bromine, giving rise to succinimide radical and bromine radical. The obtained bromine radical can react with the allylic hydrogen. So this is the allylic hydrogen. Allylic hydrogen also undergoes homolytic cleavage. So that means there will be a HBr formation and allylic radical is obtained. This is the allylic radical. So then what will happen? one more equivalent of NBS. This is a one more equivalent of NBS can react with the HBr. So here both the things, NBS as well as the HBr undergoes homolytic cleavage. Here also a homolytic cleavage. Once homolytic cleavage happens, N-succinimide radical is obtained. The succinimide radical can react with hydrogen radical, giving rise to succinimide as the product. Br radical can react with the Br radical and giving rise to bromine molecule. Okay, bromine molecule is obtained. The obtained bromine molecule react with allylic radical. Allylic radical. So this is a radical. And bromine undergoes homolytic cleavage. So bromine brominated to the allylic position and giving rise to allylic bromide as the product. So this is important, more particularly a allylic bromination using NBS. So you can also observe that there is no other product, only one product. What is the product name? Allylic halogenated products. If you are using NBS, bromo allylic compound. If you are using NCS, chloro allylic product. If you are using iodo, then NIS, then iodo allylic products are the obtained one. So with this, I will go to the next slide. So here I am taking an example. Suppose it is also possible, in addition to the allylic halogenated allylic compound, it is also observed that a byproduct. So what is byproduct? The byproduct, a bromine can add to the double bond addition reaction. So then a byproduct dibromo alkane is obtained, and this is undeserved. This is not the required one. That means it's a byproduct. And similarly, suppose a NBS, N-bromosuccinamide, if it is treated with toluene. So you can observe that this carbon is benzene carbon, and whatever the CH bond is present on this carbon is vinylic hydrogen. So vinylic hydrogen means the hydrogen which is directly attached to the double bond is called vinylic hydrogen. Okay, directly. So here this hydrogen. So what is the difference between this hydrogen is called vinylic hydrogen and the hydrogen present which is attached to a benzene ring, okay, through carbon. Okay, this proton is called again allylic proton. So methyl proton in toluene is called allylic benzylic proton. It's not an allylic, of course, it's allylic only, but since the CH3 group is attached to a benzene ring, we will call it as a benzylic proton. So what it means, when a NBS is treated with toluene, okay, the bromine does not add to the aromatic moiety, but it will add to the side chain. What is the side chain? Methyl group. So what is the methyl group? It's a benzylic carbon. What is the proton attached to a methyl group to the benzene? And this proton is called benzylic proton. So what it means? It means that NBS selectively halogenate the benzylic proton. So that means 1H from the methyl, which is attached to a benzene ring, is replaced with bromine. So giving rise to benzyl bromide. Benzyl bromide is the product. Right. So with this, I will take up one more example. Suppose a molecule contains double bond as well as the triple bond. In such cases, if we are treating with NBS, then what will happen? The bromine will add to the alpha position. The bromine will add to the alpha position to the triple bond. So that I will go to the next slide. So look here. So here I am taking propene, a triple bond. This triple bond is attached to a this triple bond containing compound contains alpha position. This position is called alpha position. Suppose this moiety is treated with NBS, then bromine will add to the alpha position of the triple bond containing compound. That means this proton is halogenated. So giving rise to alpha bromo propene as the product. And of course, these type of molecules are also called as propargyl halides. So with this, I will go to the next slide. So in the next slide, I am taking 3 kinds of proton. So I think you are aware about methylene proton, okay, methyl proton, and allylic proton. And also you are aware about benzylic proton, and also you are aware about vinylic proton. Suppose in the next slide, I am taking where there is a presence of methyl proton, vinyl proton, and also a what is called as allylic proton. Okay, I will go to the next slide. Look here. So this proton is directly attached to the double bond. So that is the reason this proton is called vinylic proton. And the alpha position to this functional group. This is a double bond. To this alpha position is this. And this proton is called allylic proton. Allylic proton, HA, allylic proton. Vinylic proton, HV, vinylic proton. And this proton is called methylene proton, CH2, methylene proton. So that means this moiety, what is the name of this compound? Cyclohexene. Cyclohexene contains vinylic proton, allylic proton, and methylene proton. So suppose, so during the photochemical or thermal reaction, more particularly in the free radical reaction, so there is a possibility of the cleavage of homolytic cleavage of vinylic uh, uh, hydrogen, allylic hydrogen, and methylene hydrogen. But which one is more stable? So usually the cleavage of vinylic proton is difficult. And similarly, the cleavage of methylene proton compared to the allylic proton is difficult. So allylic proton, it is easily to undergo homolytic cleavage and giving rise to allylic radical. Where is the allylic radical? This is the uh, allylic hydrogen abstract. This is the allylic radical. So the obtained allylic radical is stabilized by resonance. Stabilized by resonance means this pi bond undergoes homolytic cleavage and forms a double bond here and forms a radical here. So other than the allylic radical, these two means vinylic proton obstruction and methylene hydrogen obstruction does not give a stable radical. That is the reason allylic hydrogen obstruction is the stable product. So this is the key intermediate, and this key intermediate is stabilized by resonance, and that is the reason the major product is allylic substituted product, but not the vinylic substituted, but not the methylic substituted product. Is it clear? Is there any doubt up to this? Hello?
No, sir.
Okay. I will go to the next slide. So here I am taking an example. So what at all you can observe? A double bond. Adjacent to this double bond, this carbon is called allylic carbon. The proton attached to this carbon is allylic proton. And of course, this carbon is also a allylic carbon. The proton attached to this carbon is also a allylic proton. NBS means it is a known for allylic halogenation. Here, what is the halogen? Br radical. Okay, it will supply Br. It will act as a source of bromine. So suppose a Br is forming a bond with this allylic carbon. Br, you know that it's a bulky group, and a tertiary butyl group is also a bulky group. So that is the reason there is a steric hindrance. This representation is called a steric hindrance. So because of the steric hindrance, the bromination to this allylic position is not favored compared to this one. Here, so this will be the favored one. So because of less steric hindrance. But here there is a more steric hindrance. That is the reason this product forms in less quantity and this product forms in more quantity. And I am taking a bicyclic compound. So one is a 6-membered ring, another one is a 7-membered ring. What you can observe, this carbon is also a benzylic carbon, and this carbon is called allylic carbon, and this carbon is called benzylic carbon. So there is a difference between this benzylic carbon as well as this benzylic carbon, because this benzylic carbon attached to a double bond. That means this can also act as a benzylic as well as allylic. Whereas this one, benzylic carbon, which is attached to a CH2. So that is the reason this carbon or this proton is more reactive or more acidic in nature. So then when this moiety is treated with the NBS, NBS will act as a source of bromine, and bromine will form a bond to this carbon and giving rise to this product. Bromine is not attached to this benzylic carbon as well as this allylic carbon. That's what you need to remember, because bromine is attacking only to this benzylic carbon, because this is a benzylic carbon and also a allylic carbon. Allylic carbon with respect to this double bond, benzylic carbon with respect to this benzene moiety. And of course, this is also a benzylic carbon, but this is not a allylic carbon because this is attached to a CH2 group. Right. So with this, I will go to the next slide. So here I am taking one more example. You can observe that a double bond, and this is a double bond, and this double bond is attached to a CH group. This is a CH group. I think you are aware that CH group means methane proton. METHYNE, methane proton. Here there is a methane proton, and this methane proton is nothing but a allylic hydrogen, and this carbon is nothing but a allylic carbon. So what will happen when a allylic hydrogen is treated with NBS, N-bromosuccinamide? There will be a reaction between the allylic proton and NBS through radical mechanism and giving rise to bromo to this position. So that's what the product is obtained. Suppose in place of NBS, if you are taking a Br2 itself and subjected to irradiation. Irradiation means in presence of sunlight. In presence of sunlight, bromine undergoes homolytic cleavage, giving rise to Br radical. And before that, this moiety also, allylic proton containing moiety also undergoes homolytic cleavage. That means if it is undergoes homolytic cleavage means it will form a tertiary radical. This is a tertiary radical. Suppose you can also observe that this carbon is also a allylic carbon. The proton attached to this carbon is also a allylic carbon. Suppose this undergoes homolytic cleavage, then the obtained radical is a primary radical. So that means if there is a homolytic cleavage here, a tertiary radical is obtained. If there is a homolytic cleavage here, a primary radical is obtained. So you know that as per the stability, the primary radical is less stable compared to the tertiary radical. Tertiary radical is more stable. Since the tertiary radical is more stable, it can react with the Br radical, giving rise to allylic halogenated or brominated product as the product. Okay. So I will take up one more reactions. More particularly, I will take up a carbonyl compounds. So carbonyl compounds means maybe a aldehyde or a ketone or an acid. Here I am taking an aldehyde. So this is an aldehyde. Oxidation of aldehyde to a carboxylic acid. So what you can say that reaction of aldehyde in presence of light, more particularly in presence of air. So what is air? Air contains oxygen. So that means oxygen will act as a source of oxygen and air will give you oxygen to the aldehyde and aldehyde is converted into carboxylic acid. So this is only addition of oxygen and this reaction is called oxidation and here a aldehyde is converted into carboxylic acid and it's a slow oxidation. Slow oxidation means without combustion of an organic substance by atmospheric oxygen is called autooxidation. The reaction occurs when the compounds are allowed to stand in air. It is catalyzed by light, also by initiatives. Initiative means radical initiators. And the reaction can be inhibited. Inhibited means the reaction can be stopped by using antioxidants. So what are the antioxidants? Hydroquinone is the antioxidants. Hydroquinone aldehydes have the tendency to react with the atmospheric oxygen to form a carboxylic uh, acids. So this is a reaction how the aldehyde is converted into carboxylic acid. It's only the addition of oxygen where oxygen is obtained. Oxygen is obtained from the source of air and this reaction is carried out in presence of light. Light reaction means free radical reaction. So in the next slide, we will look into the mechanism, how the aldehyde is converted into carboxylic acid. Let's go to the next slide. So it is an aldehyde. Aldehyde, when it is irradiated with light in presence of initiator. The initiator may be a AIBN or may be a benzoyl peroxide or may be a acetyl peroxide. So what will happen? The hydrogen which is attached to a electron deficient carbonyl carbon undergoes homolytic cleavage giving rise to radical. Acyl radical is obtained. The acyl radical react with the oxygen which is present in a air. So giving rise to acyl peroxy radical. So this group is called acyl peroxy radical is obtained. Acyl peroxy radical can react with one more equivalent of aldehyde. How it will react? Again, the what you call CH bond homolytic cleavage. So that means H is forms a bond with the acyl peroxy radical, giving rise to acyl hydrogen peroxide. Acyl hydrogen peroxide as the product and acyl radical as the intermediate. At this moment, again, acyl hydrogen peroxide undergoes homolytic cleavage in presence of one more equivalent of benzaldehyde. Again here benzaldehyde further undergoes homolytic cleavage between the carbonyl carbon and hydrogen. So that means again there will be a formation of acyl radical. And once there is a cleavage here, this OH will add to acyl radical, giving rise to carboxylic acid. So that means two molecule of acyl hydrogen radical can undergo homolytic cleavage, can give two hydroxyl radical. Those two hydroxyl radical react with acyl radical, giving rise to two molecule of carboxylic acids. Is it clear? Is there any doubt up to this? Hello?
No, sir.
Okay. I will go to the next concept. So that is neighboring group assistance. This is also important as far as examination is concerned. So there are questions framed on neighboring group assistance in free radical substitution reaction. So what is happening here? What you can say that, what is the name of this compound? So name of this compound is called a alkyl. This we can say that alkyl and bromide. Alkyl bromide. So what type of alkyl bromide? Bromide is attached to this carbon and alpha position. Okay, this position is called alpha position. Alpha hydrogen. Okay, alpha hydrogen containing alkyl bromides. Alpha hydrogen containing alkyl bromides, when it is irradiated with light in presence of bromine, so it will give you alpha halogenated alkyl bromides. And here what is happening? It has been shown that free radical reactions are accelerated by neighboring group participation. How the neighboring group participation? That I will explain in the next slide. So here what you can observe that, so there will be a replacement of this hydrogen with Br. So that means there is the halogenation to this carbon. Okay, so that is the reason you will get a dibromo compound. And what is the percentage of yield? 84 to 94% is the product formation. And this product is formed via neighboring group participation. So in order to explain neighboring group participation, I will go to the next slide. So look here, the first step is the radical initiation. So first step, radical initiation. Radical initiation means homolytic cleavage. So giving rise to Br radical. So once the Br radical is obtained, so that will react with the alkyl bromide compound. How it will react? So the Br radical react with homolytic, what it will do? It will make a homolytic cleavage between this carbon and this hydrogen. Once there is a cleavage occurs, then this hydrogen radical forms a bond with the Br radical, giving rise to HBr is the byproduct. Once there is a radical is formed on this carbon, you know that bromine contains 3 lone pair of electron. So one of the electron, it will form a bond with this free radical. So that is how a intermediate is obtained. Thus, that intermediate is denoted as intermediate A. And since there is a loss of electron on the bromine, bromine attains a positive charge. At this moment, the liberated HBr or maybe one more molecule of bromine undergoes homolytic cleavage and giving rise to Br radical. That Br radical will attack this carbon, and this bonded, this what is called as homolytic cleavage means this the given electron is taken by the Br. So that is how a dibromo product is obtained. Is it clear? Is there any doubt in neighboring group participation? Hello? 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 Is
Yes,
there,
sir.
is there any doubt in neighboring group participation?
No, sir.
Okay. Okay, that means what you need to do, if you are understood about the intermediate formation. So this intermediate is formed by the lone pair electron of the bromine and the radical formed on this carbon. So that's what you need to remember. The formed intermediate react with the bromine radical. So that means bromine undergoes homolytic cleavage, and this radical react with the radical formed between the homolytic cleavage bond between this carbon and Br plus 1. Right. So what I will do, maybe at this moment, uh, if you don't have any questions up to this today's class, maybe I will stop at this stage. If you have questions on today's class, you can ask me.